My name is Eric Kaneda, and I am an engineer at Risk Zero. And I have a question for you today. If knowledge is power, what is zero knowledge? Well, let's start with what a zero knowledge proof is. Now, kind of like the layman's explanation is that zero knowledge proofs are problems that can be that are typically involving multiple parties, where one of the parties that wants the problem solved gets the solution without knowing any more than necessary. So, for example, this is called the two-color ball and two-ball problem and the colorblind person. Now, this problem is near and dear to my heart because I'm partially colorblind. So, anyway, the problem is that let's say that there are two different colored balls, and there's a person that cannot see colors very well. And so the person is trying to determine if the balls are of the same color or the different colors. So what happens is like a person hands me the balls, and I will put them behind my back, and I will pretend to switch them or maybe not switch them, and then ask the person who can see the colors if I've switched them from the initial configuration. So now I will do this repeatedly and record my results until I am convinced that either A, the balls are of the same color, or they are of different colors. Now, notice that throughout this problem, I am not getting the information about what color the balls are. I am only trying to get the understanding that they are different or the same. So that is a quick rundown of what a zero-knowledge proof is, but why does it matter? Well, fun fact is that it takes zero-knowledge proofs to unlock verifiable computing. And in the past few years, this has been a very, very hot topic. And so there has been a lot of things that have been said about what zero-knowledge proofs can do, what verifiable computing can do. And like the future kind of looks like this. And people have said that it could accomplish many, many things, such as privacy, security, elections and governance, identity management, maybe even securing power plants, nuclear disarmament, and even like anonymous ad auctions on your browser. But a lot of times when we try to dive into this space, the world kind of looks like this. All right, with all these terms such as SNARKs, or finite fields, or PLONKs, or polynomials. Well, it sounds like math. Constraint polynomials. And Fiat-Shamir heuristics, or Fry, or Montgomery form, or deep Bali, and I think you get the point. This seems to be a very complicated space, but what is verifiable computing? Well, let's start with a program, okay? And we have a special virtual machine that we'll call the zkVM. Now, the zkVM will take the program and their inputs and then runs the program. And then as a result, it will generate a receipt. The receipt can be then verified by an outside entity to make sure that the computation was done. Okay? So now let's take a closer look at receipts. The receipt has three parts. So it has what we call at Risk Zero the image ID, which is the SHA of the executable code. You can think of it as like a unique identifier that represents all the code that is being run. And two, a proof that an executable code was run, as well as the journal, which we can think of as the result of the computation. Now, the result of the computation is up to the program itself. And so the seal indicates that the program that is indicated by the image ID was run correctly and produced this result in the journal. Now let's take a closer look at the zero-knowledge virtual machines. Like many virtual machines, there are like a lot of things such as like memory and whatnot, but one of the major differences between a regular virtual machine and a zero-knowledge virtual machine is that it has a circuit. And this is where all of the complicated mathematical concepts used to enable zero-knowledge proofs lie in this system. And in particular, for RISC-0, this circuit it implements a RISC-V assembly emulator. So RISC-V, and I had some people who weren't familiar, but assembly is like the code that runs on the actual CPU. Now, and a little bit of a clarification here, the assembly emulator, although it is software, okay? So now let's put this back into our picture now. So we have the zkVM, and all the complicated math goes in here, which means that the programmers do not have to be encumbered or think about polynomials or finite fields or other zk math unless they really want to, and that sounds like a cool application. Now, because the circuit enables or it is interpreting RISC-V code, it means that the programmer can use programming languages with compilers that will translate from source code to RISC-V code. So now let's take an example here that uses these concepts. So I was on a flight, and this is an actual story. I was on a flight with my partner, and we were bored, so we started playing an in-flight backgammon. So it's like, you know, she was on one screen, I was using another screen, and there was an issue. There was a bug in the random number generator used for their dice rolls, which meant that on each game, the numbers that came up as dice rolls were the same. So it's not like, so each game had like the same set sequence of numbers, which was kind of like nice because I won like 10 games in a row. And shortly after, and she was actually teaching me backgammon, and so I love backgammon in this game, right? Shortly after we got home, we purchased the backgammon board, and it turns out that true randomness makes the game more difficult. So now, as inconsequential as this may seem, this is an example of us humans, you know, not trusting systems. The reason why we stopped after 10 games was because my partner knew, she lost trust in that this in-flight video game was going to give us a fair game. So how can we trust in-flight backgammon again using these concepts? Well, so we have some, you know, assuming that we have some sort of computer that is managing the games, right? We can have the server run these computational proofs with a receipt that contains some sort of information about what kind of random numbers are being generated. Now, this also implies that we're placing trust on the zkVM itself, which might not be good. So there might be more creative ways, such as the players themselves submitting their own random numbers, and maybe like there can be some sort of game theoretic way to make interesting results so that the gameplay is more fair. And as you know, and because the receipt is submitted, like each of the players, assuming that they're on different nodes, can verify the computation to say, hey, this is a correct and desired outcome of the game. Another example where we can apply this is on current blockchains, where one machine wins the transaction and does the transaction blocks, which means like they execute a lot of smart contract code. What happens then is all the subsequent machines will start doing the same work over and over and over and over again. But with this approach of verifiable computation, what we can do is instead the machine can then submit a receipt that then can be verified on all the other nodes. So to wrap up, let's go back to this question. If knowledge is power, then what is zero knowledge? And in my view, zero knowledge enables verifiable computing, and in turn, and today we have zero knowledge virtual machines that are easy to use for any programmer without having to know a lot of zero knowledge mathematics. And three, by using these technologies, we can build more secure and trustable environments. So where are we now? In the past, there have been a lot of mathematical research that has been done, and this is, of course, ongoing at all times. And we have this future that is like a ZK-enabled future. But we are here now with all these tools that enable us to write ZK apps. So, and execute them on services such as Bonsai. So I encourage all of you to check us out, and thank you for your time.